The following program is brought to you by Caltech.
Good afternoon. I can tell from the discussions that the speakers so far today have really excited people about the ideas and the challenges that we're facing around the country with regards to energy, and that there's a lot of ideas on how to solve it. Probably more ideas than we need, which is good because we're not sure which ones are actually going to work out right. I am pleased to introduce Jose Andrade, who's an associate professor in the Division of Engineering and Applied Science. Professor Andrade joined Caltech after 4 years at Northwestern University as an assistant professor in theoretical and applied mechanics. He obtained his PhD in 2006 from Stanford University in the area of geomechanics. His research interests lie in the area of computational mechanics with applications to problems at the interface of physics and mechanics to develop predictive analytical and numerical models for porous materials. These include rocks, foam, bones, etc. Professor Andrade is the recipient of several honors and awards, including the 2006 Zeinkwitz Medal in Computational Mechanics, the 2010 NSF Career Award, the 2010 Young Investigator Award from the U.S. AFOSR, and the 2011 Arthur Casagrad Career Development Award from ACSE. His work is currently funded by the NSF, the U.S. Department of Energy, and AFOSR. Please welcome Professor Andrade. Thank you.
Thank you very much for that very kind introduction. I don't know if the mic is on. It seems like it is. So it's a pleasure for me to be here. I'm actually surprised to see an audience at this time of the day on a Saturday. But my role here is to show you a little bit of what we do in our lab. We run the Computational Geomechanics lab here at Caltech. I'll tell you what geomechanics roughly entails. But today, given the topic that you've been discussing, I want to show you what many people forget about in the energy discussion, the role of geologic materials in the energy and sustainability question. There's a lot of excitement and hot air about new sources of energy and what the future brings. But I hope to show you a little bit of reality and show you that the present will control a lot of the future, at least for the next few decades. And that there are better ways to do the future. So in trying to address that, I'd like to show you some energy issues that we're facing and how geologic materials enter into those issues. And then I'll get into the fundamentals of the kind of things that we're interested in, and I'll show you how important these things are in the energy problem and sustainability. So that I'll address things like flow in porous materials, so you can imagine why flow is going to be important in many applications. I'll show you the formations in porous materials and why they're important. And then I'll close with cements, the things we do to build a new infrastructure and a new built environment around the world. And hopefully, after my talk, you'll get a sense for how important these materials are and their key role in the challenges that we face. So let me first tell you a little bit about what we do in our lab. So this is the way we see the world, or a physical phenomenon. Right? You can do experiments. Many people do experiments at Caltech. You can do field observations. You can go to the field and actually take measurements. Or you can do simulations and theory. We focus in our lab in the bottom two. We do simulations and theory to tackle physical phenomena. And we collaborate with people that really know what they're doing up here. Okay? I'm not allowed to enter laboratory facilities. Okay? I may break something. So I'm a theoretician, so a lot of what I'm going to show you today is theory, simulations, but it's not science fiction. I'll show you experiments right next to them, not conducted by us, but conducted by people that really know what they're doing. And you'll see that these models are doing something interesting. But before I show you what I came to show you, let me show you a little bit of exciting things that we're doing in the geomechanics group besides energy and sustainability. So this is a map of Mars. That's, in fact, a topographic map of Mars showing elevation differences. This blue area here is a lake, which is going very deep. And this white areas here is peaks, like a mountain. The difference between the white regions and the blue regions is 20,000 meters, okay, so about 20 kilometers. This mountain here is 12,000 meters, so about 12 kilometers. Everest, for your information, is about 9 kilometers in height relative to sea level. Now, we're sending these little rovers, right? There are 2 rovers now on Mars right now, Spirit and Opportunity, and there's a new rover going out at the end of a year. And these little rovers are geologists. They have to map the surfaces and study the surfaces of Mars to collect data that is sent later to the Earth. In fact, a future mission will collect a sample from Mars and send it back to Earth, okay, a sample of geologic material. In order to make this mission successful, the rover, the geologist, has to survive. It has to go places. Let's say you want to go to that peak, take a sample and come back to base. If that doesn't happen, the mission fails. So it is our job to understand the interaction between this little rover. So this is a simulation of a wheel of a rover and the Martian geologic material, in this case, Martian real soil. And understand that interaction because, as you probably know, there's one of the rovers is stuck now in Martian soils, and it's useless, okay? And it's not good when you lose a multi-million-dollar mission up in Mars. And in order to do that, this is the kind of things that we do. We go from very small scale, particle scale physics all the way to, say, a rover scale simulation of the actual vehicle. And we really want to capture all the physics across the scales. And I'm going to be showing you that same philosophy for the energy and sustainability approach. And along the way, even though we do the modeling part, we collaborate with people that do really beautiful experimentation that keeps us honest. Okay, so this is, for example, the Mars yard at JPL. And you see the new Mars rover in real sand, in real terrain, trying to crawl up, in trying to model the same conditions that you would face in Mars. So the role of these models is to really give you insight into a physical phenomenon that otherwise is too difficult to understand, like being on the surface of Mars. This was my first love. This is what got me into grad school. This is a picture of the 1964 Niagara earthquake. Last time in seminar day, I showed some of the things we do in liquefaction and related to earthquakes. This is a really beautiful, well, you probably don't think it's beautiful when your building collapses, but it is really a beautiful phenomenon that occurs. It's called liquefaction. It's an instability. This happened right after the 1964 Niagara earthquake. It was like a 6.4 earthquake or something close to that. And that created what's called liquefaction, which is a transformation of your soil underneath from a solid behavior. You know, this building is sitting on a solid foundation, hopefully. But then an earthquake comes, it excites the foundation, the soil underneath, and that soil starts to behave more like a fluid than a solid, and things give. And there's nothing wrong structurally with those buildings. They just collapse because their base was not able to carry the loads anymore. So that occurs in the field, it occurs in the lab, and we're very interested in coming up with models that can capture and hopefully one day predict those kind of instabilities for obvious reasons. A very close relative to liquefaction is the landslide. This used to be a highway in Taiwan. These things occur very frequently during the El Nino season or the rainy season, and they occur a lot in California and throughout the world. And once again, just like liquefaction, there are instabilities. They happen all of a sudden, and they're unpredictable. No one can pinpoint when and where these things are going to happen. Okay? There are no models that can warn you that you can have this disrupting your infrastructure. And as you saw in the previous picture and in this one, clearly these things interact heavily with your infrastructure and they disrupt life. I mean, this is very inconvenient for this guy that wanted to go home. Very inconvenient. And as climate change advances, as we believe it is, these things will become more and more frequent, okay, unfortunately. So having the ability to pinpoint when and where they will occur is going to become more and more important. Okay, but let's start getting more into the theme of the talk, which is sustainability and energy. So, okay, so just to reiterate, why are landslides interesting in the term of or in the light of sustainability? Climate change will exacerbate landslides. There is no escape, okay? The more it rains, the more landslides we'll have. They do interact intimately with our infrastructure and humans, obviously. The costliest landslides, for example, in the United States, happen during El Nino season. Okay, so it's tightly correlated to to rainy season, okay? And they're just, again, beautiful opportunities to look at this mechanics and physics boundary of this very complex, very beautiful materials that I'll show you play a very key role in our lives. Let me say a few words about cement before we start getting more and more into energy. So you might not know this, but a fourth of the energy consumed and the CO2 produced in the world is due to producing primary materials, okay? Steel and cement, for example. Okay, a fourth. Concrete is now the most widely construction material on Earth. Why is that? It's cheap, right? It's very cheap to produce. Anyone can produce cement anywhere in the world, okay? And it's extremely versatile. Okay, I was reading a book recently. There's a guy proposing that the Egyptians built the pyramids using cement. Okay, I don't know about that, but I mean, it's an interesting notion that it is really a very versatile material, and then it would have made the building of a pyramid a heck of a lot easier. So concrete is the most widely construction material on Earth. So if you make a small impact, a small change in its CO2 footprint, for example, you can have a very big impact. Okay, so, because remember, you're using a fourth of the energy in CO2 to make these materials. China, not the United States, China is the largest producer and consumer of cement today, consuming about 50% of our cement. And if you add the other BRIC countries, Brazil, India, right, it's probably coming up to 80%. So unfortunately, in this country, even if we produce the greenest concrete ever, we're not going to make that big of an impact. It's really the BRIC countries that will make an impact if they make any changes. Okay, and about 5 to 10% of our CO2 emissions are due to cement manufacturing and transport. Okay, so this motivates us to understand, and I'll show you some of that, the nanostructure of cements, so that one day we could make small improvements in that nanostructure, engineer that nanostructure in a way that allows us to create greener, newer cements that are better for not only our infrastructure but also our environment. So we'll talk a little bit about that. Okay. So let's start getting a bit more serious here. So what are some of the really big energy issues that we're facing here? So let me show you some data, okay, that you may or may not know. So energy consumption correlates directly, right, with population growth and quality of life. Okay, most people know this. And I'll show you a graph of the correlation between energy consumption, for example, and quality of life. The current world consumption of energy is about 16 terawatts. And in order to keep the growth that we need for our civilization, we need to increase our production at about 1% per year. If we want to encourage growth in the developing world, say in Brazil or in China, we need to grow at 2% per year. Now, a growth in 1% a year, which is, I think, as an engineer, is rounding error, needs about 160 new nuclear plants. Okay? A growth of 2% is twice that. And that's when people say that you would have to build a new nuclear plant every day in order to sustain growth. Right? Many people quote that number. That's where it comes from. Right? Can you imagine that? I mean, so that you know, there are 500 nuclear plants in the world since the invention of nuclear power. And here you're talking about building 160 new nuclear powers just to keep growth, not to encourage it, just to sustain growth. So this is the part where I claim that new energy alternatives are very exciting and very promising, and we must continue to look at them. But we must not forget that they will not make a big difference in the next couple of decades. And that's, I think, a fact. And we need to face that. And when we face that, then we clearly need all sources of energy for the next 2 to 5 decades to be on the table. And then the question we have is, how do we make these sources of energy environmentally friendly, right, so that we can continue to use them? Because clearly they're making an impact in our environment. So here's the slide that shows, I don't know if you've ever seen this slide. The first time I saw this slide, I was really shocked. This is a slide showing a map, a graph, let's say, showing human, it's a Human Development Index, HDI. Okay, this measures quality of life, per capita energy consumption. Okay, and you see some of the key players. The United States is all the way up here. Okay, of course, we have very good quality of life here at a very high cost in energy per capita. Right? Only Iceland consumes more than we do and has about the same quality of life. But check it out. Italy, for example. These guys are having a pretty good time. Pretty similar to the United States, right? At a third of the energy consumption per capita. Why? Maybe the Mediterranean, I don't know, olive oil, wine, I don't know. Something is making a difference, right? France is doing pretty good. So clearly in this country we're consuming a lot of energy. Yes, we have a very good quality of life, but once you get all the way up here, making a difference in your quality of life takes a lot of energy. Okay, so we could make a big impact in our energy consumption by just reducing the amount of energy we consume, and we wouldn't lose a lot in our quality of life, right? Now, the scary part is, look where Brazil is. Where's China? Do you see China? No, it's not on this map. Here's Russia. Okay, and China, I think, is somewhere over here. These guys are moving up, right? They're trying to catch up with us, and they will. So that means that they'll continue to suck more and more energy, right? We're stuck here. We're not going to move too much. But the other guys that come down here that want to improve, they're going to move up. And they're going to be the ones demanding more energy. So just in case you want to know, so Human Development Index is made up of 3 other indexes, right? Life expectancy, education index, and GDP index. And you can find all of this data online. So I guess you're starting to get the point that I'm trying to tell you here, that we need improvements now to the sources of energy we have now, because we will not be able to replace them now. Right? It will take time. So in the meantime, we need to do something about our energy. So one of the big new players, at least 8 years ago, was CO2 sequestration, and it continues to be one of the big promises, at least for fossil fuels. Right? So let me tell you a little bit of what CO2 sequestration is. So the idea is that CO2 levels in the atmosphere are correlated with increases of average temperature in the planet. And what people are proposing is to take that CO2, instead of pumping it into the atmosphere, pump it down into existing or empty oil reservoirs. Okay, so there used to be fluid down here. You are either exploiting oil from it anyway, or it's been emptied, and you have some empty spaces down here. You might as well use it with something, with another fluid. Why not pump CO2 down there? This geology is already used to hosting a fluid anyway, so you can imagine that this is a very natural candidate to store a fluid. So here's the sketch of the idea. So you would come into an existing or new well, right? Drill down to the geologic formation where oil existed or where oil still is, and pump CO2 at very high pressures and very high volume. Now, this is not a new technology. The oil industry has been doing this for many, many years. Okay? But they have been doing it for a different reason. They have been enhancing oil recovery doing CO2 pumping. So you would come here, pump CO2, so you would increase pressure here. And let's say this is a producing well, oil well, that will allow you to pump oil out at a faster rate. Okay? And this was a trick used, and it continues to be used. Now here the proposition is different. It's not to enhance oil recovery, is to pump it down and sequester it. Okay? And that's where the word sequestration comes from. You want to keep it down there. Now that sounds great. The problem is that when you do this, many doors open. The first door that opens is you pump this CO2 down here, you will change. There's water all around here. There's groundwater that eventually may make it to the surface. So the first problem that you have is that you change the chemistry of the water all around you. Okay, and that may have, nobody really understands the complete impact of that on the environment, okay, the release of CO2 or the mix of CO2 with our water. The other problem, so you have reactive geochemistry going on at the pore scale. That reaction as well will change the mechanics of this rock, and it may change it mechanically. So a rock that used to be able to sustain a certain load may not be able to sustain it anymore. Okay, and you may have collapse. And that has been reported in many cases where CO2 has been injected. You may induce seismicity. You may have a fault zone over here. And because of pumping CO2, you change, again, the stresses around this, and you may induce seismicity. And again, that has been reported, that has happened. But the most problematic part is that in order to keep CO2 down here sequestered, you're going to have to keep it down there for centuries. And that means that you don't want any leakage from here. And these formations are completely heterogeneous. I mean, who knows what's down here, right? How can you characterize and how can you assure that this is not going to have, say, 1 to 2% leakage per year? So it's a big issue. And therefore, the understanding the coupling between mechanics, flow, and chemistry is going to be central if this kind of applications is to really survive. By the way, Taiwan is already doing this. I was in a meeting with the Taiwanese, and they're not thinking about it. They're really going ahead with it. And as a technology, I predict that it will take place, but it will be done empirically. It will be done without really understanding what's going on, and that's not a good thing. Okay, so this is a pie chart that I show people to sort of bring some reality to the table. This is a pie chart of our energy sources at this moment, right, from DOE website. 85% of our energy comes from fossil fuels. If you add the 6% from nuclear, that's 91%. That comes from sources of energy that are not perceived as environmentally friendly, to say the least. How long do you think it's going to change? How long do you think it's going to take for that pie chart to really change? Any guesses? I mean, let's say, how long would it take for this 9% that includes all the new energy sources to go from 9 to, say, 20%? 20 years? Okay, 2 to 3 decades. Okay, what do we do in the meantime with all the energy that we need to produce? Right, with this 1% increase, with this 2% increase in energy that we need in order to keep growing in this planet. Right, we're going to have to continue to open this pie chart, right? This 91% will have to continue to be there. And that's not sustainable, right? So CO2 will have to happen sooner or later. And you want to capture in decades and store for centuries. Okay, you want to go into these formations as potential locations to make these injections. And you have to inject huge amounts of CO2. Okay, just huge, 7 to 15 gigatons per year. Okay, by the end of a century. Okay, and then you have another problem. You have to continue to have nuclear, and you will have to have a repository. Can you believe that there isn't a single repository in the world where you can go and store nuclear waste? None. Now, remember Japan, people started to really get freaked out about nuclear because there was a problem with the Fukushima plant. Now, the problem is not the Fukushima plant. The problem is that there is no place to take that fuel after they've used it and store it. Right? And it's sitting there in these pools, and the same happens in this country, right? We have El Diablo nuclear plant is sitting there with a pool of used fuel, right? Just sitting there.
Yeah, on-site storage. That's the solution so far.
Well, sure, but you need a storage place, right? Where are you going to put it? Just leave it there.
Well, keep the pool maintained forever.
But the Swedes and the French dispose of their nuclear waste. The Swedes put it down.
They put it down in the water, right?
Put it in little pellets and bury it somewhere. I don't
That's
think
right.
that's a very good way. The Swedes are doing a pretty good job.
That's right. But I honestly think that we're going to have to face the idea of coming up with some sort of repository where it's on site or where it's somewhere else. You're going to have to store it safely somewhere, and there are ways to do that. So again, the idea that hydro-chemo-thermo-mechanical coupling is going to be important here is undeniable. Let's talk about natural gas. The new blue-eye boy, right? I mean, this is like, there's so much excitement about natural gas now. I'm excited about natural gas, but I'll tell you some facts that are not that encouraging about natural gas. So the very beautiful thing about natural gas is that the U.S. has 2 times worth of Saudi Arabia in terms of natural gas. And here we're comparing natural gas versus oil. Right? So we have plenty of natural gas. And this is a map here of the geologic formations called shales, where we have natural gas in this country and where we're producing natural gas currently. Okay, so there's plenty of it. Okay, enough to solve our energy problems for, say, a couple decades without depending on any foreign oil. Right? Now, the problem is that natural gas, another thing that is nice about natural gas is that the cleanest of the fossil fuels is the cleanest. Right? When you see CO2 footprint, for example, it's very nice. So it is appealing. Now, the problem is that it used to be in these formations that were thought as irrecoverable, right? This shale formations, I'll show you a picture of what a shale looks like in the microscope. The shale formations are extremely tight formations. They don't have a lot of pores. So pumping out gas from these formations is very difficult, okay? Very, very expensive. So they were thought to be irrecoverable. So people wouldn't count them in the potential pie chart, but things have changed, okay? Most of the natural gas, as I said, in this country is in these formations called shales. And the most promising formation, I was sitting last night with some folks from the Northeast. There you are. So here, you guys are in luck. You have the most promising shale formation, the Marcellus, right? It's right there. Although people that live in that area are not very happy of having that formation there because.
The USGS now has revised their reserves about half of what they said a couple of years ago.
That's right. So what changed? What was the game changer in terms of natural gas, right? These were supposed to be irrecoverable resources. Why are they now so exciting? So there are a couple of new well, they're not really new, but let's say that 2 technologies have changed dramatically recently that have enabled natural gas to really become a player. The first technology is called horizontal drilling. Okay? It used to be that all your wells had to be vertical. Okay? And everybody, that's the way we did wells, right? You would go to the formation down here and pump the oil out. Maybe if you were pretty smart, you would do slanted drilling, right? But recently, now you're able to go not only vertically, but actually have an elbow, a 90-degree turn, and go horizontal. And that changed many things. The other change that was dramatic was the, let's say, perfection or improvement of what's called hydraulic fracturing or fracking. Right? Hydraulic fracturing is very simple. You go into a well, whether it's vertical or horizontal, and you pump water at very high pressures, right, until you break the rock around you. So this is an example of that. So you notch it a little bit, right? So you weaken the rock in certain locations. And then you insert a fluid, usually water, and you pump it at very high pressure, and you break the rock around you. Okay? And by doing this, you enhance the ability for other fluids that might be around this rock to be extracted very easily.
Do you know what the pressure kind of range is?
No, I don't have a number on, but I'm sure we can find that out very, very easily. So remember, horizontal drilling and hydraulic fracking, or fracking, changed everything. Now, here's a cartoon of how hydraulic fracturing is done, and we'll study fracturing a little more. So here's your well. Here's the notch that you did at the beginning. Now here's your fracture now, or fissure. In order to keep that fracture open, right, you pump the water, you pump the fluid, you open up a crack. But that crack doesn't remain open unless you continue to press on it. You continue to apply pressure. So what these guys do is they inject sand at the same time. They inject a mixture of water and sand, and the sand acts as a propellant, right? And it just keeps the water, the crack open. And we'll see that there are implications of injecting that sand. So you open a crack, you inject sand, you keep it open, the crack, and then you can extract whatever fluid, in this case, natural gas or oil. In fact, again, hydraulic fracturing is not new. It's been used since the 40s, okay, for oil extraction. It's just that it has improved a lot. And With this horizontal drilling now, it's a game changer because now you can go really, remember your formations are horizontal. Here's where your oil or gas is, the Marcellus Shale. Right? It's a horizontal formation. So if you can access it horizontally and frack it horizontally, right, you can access kilometers of formation that contains gas, as opposed to having, you know, who knows how many vertical wells in order to access that. So that was really transformative technology. Okay, so why is it a bad word to say fracking? You know, what's the problem with this? So here's a picture of shale. So from, say, millimeter to centimeter scale to the nanometer, roughly, scale. This stuff is clay, effectively. Okay? Clays are very, very impermeable. Getting water through clays is very difficult. In fact, they're considered as impermeable as it gets in terms of geologic materials. Okay? When you want to seal something, you put clay. Okay? So shales are not very amenable to extraction or injection of fluids. Yet people invented fracking exactly because of that, to enhance permeability. Okay? But doing it vertically wasn't a good way to go. So essentially, for natural gas and oil production, okay, fracking is used to increase permeability. That's it. That's why you need fracking. You need to enhance the permeability, and that made these irrecoverable formations all of a sudden recoverable. Now here's the sticky part. 3 million gallons of water are needed for every well where you do fracking. 3 million gallons per well, on average, right? Things fluctuate. Now, of that water, 98% is water and sand, but there's a small fraction of that volume that contains chemicals, right? And for some reason, the companies that do fracking don't want to release the list of chemicals that they pump into that, right? I don't know why they would do that. So that's the sticky part. You're using millions of gallons that have been contaminated by 2% of chemicals that are not of public knowledge, right? And people start to feel uneasy about this, right? I'm sorry, what?
I was reading the paper that some of the people that disclose what the chemicals are.
Some people have volunteered to disclose those chemicals, but I think it should be a law to disclose them, and I think Congress is working on that. But I think they're finding quite a bit of resistance, as you can probably imagine.
3 million gallons is an issue too.
Oh yeah, it's a huge amount of water. But if it was clean water, it wouldn't be that much of an issue because you could reuse it, perhaps, right? But if you
permits to do this without disclosing?
Oh,
that's a great question. I don't know.
depends on where you're at. We're in upstate New York. That's a big thing right now on the Marcellus Shale. In Pennsylvania, each of the companies had to go in individually. And initially, when the companies went in and got the permissions, people really didn't know what the fracking was about.
Mm-hmm.
And then they
Right.
started to experience some issues, and now they're having to go to each individual county and state in order to get approved.
Right.
And it's not going easily at all.
Fair question, Rebecca.
Can you speculate for us on what chemicals might these be?
No.
No
No. I work for Schlumberger. No, I'm kidding. No. Well, I can tell you what the intended use of those chemicals is. Okay, so the intended use is to allow the sand to get into these cracks, right? To change the viscosity of the fluid, okay, of this mixture. That's one use. Pardon me?
Surfactants or lubricants?
Right, they serve if you want to see them as lubricants. The other use they have is these formations have cementations. They have cementing agents. They dilute some of those cementing agents, making fracking again more friendly, let's say. So clearly they have a use, okay, and companies are very protective about what exactly they're doing with these chemicals. And that's the sticky part of fracking. Uses a lot of water, and that water gets contaminated with chemicals that are not disclosed to the public, right? But here, half of our natural gas consumed today in this country has been produced in the last 4 years. So you can see how much energy there is in these formations, okay, and the potential they have. They're not growing at the pace of alternative sources of energy. I mean, in 4 years, you can have half of the production of this country produced from this formation. So the energy potential is there. So my message to you here is not to panic and not to dismiss fracking. That's not the point, okay? The point is to understand how fracturing occurs in these formations and do it in a clever way. That's a Caltech way. I mean, you wouldn't dismiss it. You would just do it well, right? I mean, why would you just get rid of it? There's a lot of energy down there. If you could just extract it with, say, less water and not contaminate that water, why would you do it? Right? You need it for growth anyway. Yes, sir.
Hasn't the fracking contaminated the water in some areas, for example, New York City?
I mean, yeah, I mean, it depends on how you define contamination. If you mean mixture of that water with the groundwater and surface water, yes, there's been mixture of water. Now, how contaminated that water is, that's where the debate starts, because what is that 2%? What are those chemicals? How contaminant they are? So, right.
Are there heavy metals in shale? A lot of other contaminants?
There might be. It depends on the formation. Yeah. So, but I mean, it's clear that every time you pump a fluid, you're dispersing things, right? And your probability of sending things back to the surface that you didn't want, whether it's gas or some other substances, increases, right? I mean, every time you're disturbing something, for sure, you can get some surprises, but it will vary from formation to formation, right? Yes.
What is the lifespan of a given, an average lifespan of a given well? For example, 3 million gallons of water, over what period of time, and what is the equivalent energy generated out of a well?
Yeah, I don't have all of those numbers, but this is per well, to make the well produce, right? And to make the well, to allow the permeability to occur. Now, later you could decide to do more fracking in order to enhance it further, because
How long does a typical well stay operational?
well, wells can stay operational for decades, right? I mean, they don't have to shut down in months. I mean, it could be, I mean, but it's not necessarily that case, right? You may need to enhance more. You may want to drill more around that initial well, okay? So, I mean, it is clear that the expanse of water and the potential contamination is there. I mean, that's undeniable, right? And that's something that we need to keep in mind.
But the energy generated
Oh, I mean, you could argue that the benefits of that are tremendous, and that's where the debate.
so many years out.
So on this fracking, is it, from a science viewpoint, is the contamination issue that you have to truck the water away, the water that comes back up to the well, or that it gets to drinking water? I heard that drinking water is typically a couple thousand feet separated, you know?
Yeah, so that's a great question. So this something that I did not say, and that it is important, is that fracking and this exploring of this shale formation happens at thousands of feet below the surface, right? Usually 10,000 feet. And your drinking water is up here, right? So that's one of the big arguments pro fracking is, look, we're really doing things down here. Don't worry about it. Up here, nothing is going to happen, right? It's too deep. It won't affect anybody, right? So yes, it does happen tens of thousands of feet under the surface, and your drinking water is really up here. So there is quite a bit of a distance there. Let me.
How many of you seen water flowing from a faucet, which was ignited?
Yeah, I saw the 60-minute program. Yeah, I did see that.
Plus, there's a lot of leakage of methane.
Yeah, but when I'm going to stop there. I did see that.
The point you made about clay is clay typically forms the cap over formations,
Right.
which is the reason you have oil wells to start with. What's the risk that you fracture the actual cap for your formation and then lose the very product that you're trying to get?
Well, I think the general statement is that every time you're fracking something, every time you're changing something mechanically, you're opening the door to things to change. right? And whether it's oil leaking up or creating seismicity or weakening that formation to its ability to sustain loads, I mean, you're opening things to change. And what exactly is that going to bring is something that is difficult to establish. And that's why that's a great way to get to my punchline here, is that all of these applications, all of them, will require fundamental understanding of what's going on between the flow along these porous materials, their deformation, right? You're clearly deforming them. You're clearly changing them by applying pressures to it. And you're really changing the chemistry. And these things are coupled. They're tightly coupled. They're very complex. And people forget about these things when they're talking energy, right? Everybody thinks that energy is solar panels, right? And it's not. I mean, not for the next 2 to 3 decades. There are other issues that we need to start to get serious about. Yes, sir.
Coming from an oil company, I have perhaps a prejudiced view. Actually, I don't think I do. I can answer a couple questions or make a couple of comments that might help a little bit.
Mm-hmm.
A lot of the early fracking was done by very small operators who did not have much experience in what they were doing. They did a lot of sloppy things. They did a lot of bad things. Stuff you are talking about today at the higher depths, they were not doing that. They were doing stuff on the surface.
Service, yeah.
The things that are being done today at 10,000 feet with good surveys and different techniques, can you guarantee anything? Probably there's nothing you can guarantee it 100%. The one picture is one picture. It's not from anything that was done correctly. It was done from things that were done incorrectly. If you make a bunch of mistakes, you screw stuff up. If you control it, now it has to be controlled. And I think the idea of better permitting is absolutely necessary.
Yeah, I think
there's a lot more knowledge about what's going on.
I think that's a fair statement, and I think that brings us to the key point here.
Companies doing it now have a great deal of additional knowledge of what's underground. They do understand geology. They've made detailed studies of the chemistry, and they do have some idea what they're doing.
Yeah, I think they're. I think they're better.
We will tell you.
Look,
We
I
will
think.
tell you if you'll listen.
I think they're better. It's undeniable that there are better technologies and we have a better understanding, and that's a good point. The key here is not to dismiss these technologies or these sources of energy, is to make them safe. Okay, and that's undeniable. Now, are they safe now? No, I don't think so, and I don't think that people completely understand what they're doing. And I'm an engineer, you know, and I know that when you do things in engineering, you need to get the job done. But in order to do it at the scale we need to do it for this new applications, you really need to understand what you're doing, and that requires fundamental understanding. That's my message here. Don't dismiss the technologies. Don't dismiss these possibilities. Just, you know, press people to invest more in research so that we can understand what's going on, so that we can have safe fracking and safe CO2 sequestration. Okay, so. We're getting close to 5:30. Let me hold on to questions, or to 4:30. I'm sorry, and we're going until 5, right? Okay, and I want to leave plenty of room for questions. So how about this? How about we get into some of the modeling things that we do, and then we answer questions again at the end. Okay. So here's a picture of what we call families of geomaterials. So this is a rock. Sandstone, classic rock for many of our oil reservoirs in the United States. Okay, sand, you know, and this is cement or concrete. Okay. Now, the interesting thing about these materials is that they may seem to you very different, but in reality they're not. They share a common structure at what we call the grain scale. So this is the sand grains, right, from a tomography image. These are the sand grains in the sandstone. The black stuff is empty space. The light areas are grains, okay? And here you see that there's a granular structure in sandstones, in these rocks, granular structure in sands. And at the nanoscale in cements, there's also a granular structure, what we call a globular structure. So these guys interact with each other, and they're the ones that determine the mechanical behavior of these materials all the way at the field scale. So one of the challenges that we face today is, and the opportunities at the same time, is to go down to these scales where the material behaves in a rather fundamental way and understand how that how the mechanics happen at, say, the nanoscale for cement, and manipulate that scale to do cements in the way we want them to do, or the way we want them to perform, say, at the lab scale or at the field scale. That's a concept of multiscale that we apply in our labs, and it allows us to look at these materials as with a unified view, rather than, oh, let me look at concrete separate from sand, separate from sandstone. We look at all of these materials as the same material in a way, because fundamentally they're the same. And then we extract information from one scale to the next in order to get the information that we need for better engineering practice. So let me just show you cartoons and sketches of the modeling tools. So the way we do this is that we view these materials using mechanics or physics. These are materials that are porous. So the orange things here are, say, your solids. Inside those solids, you have fluids in blue here. They deform. Their deformation creates deformation of the solids and also flow of the fluids. And that's controlled by partial differential equations. I couldn't get you here to Caltech without showing you an equation. So I had to show you some equations. So you solve these ODEs or these PDEs that control the behavior of the material that is interacting with the fluids, in this case the porous materials, right? And you need to do this using computers usually, because these equations are pretty difficult. Now here's a key issue. It's called constitutive theory. This kind of theories tell you how the material behaves. For example, one of the constitutive theories that is typically used, and I'll show you some of that, is called Darcy's law. It tells you how fluid flows through porous media, right, due to changes or gradients in head or pressure. And it's controlled linearly by this coefficient here called permeability. So when you hear people speaking about permeability, they're speaking about this constant that relates how much change in head or pressure you need in order to push a fluid through a porous material. The more permeable you are, the easier it is. The less permeable you are, the more difficult it is. These laws, so-called laws, are typically obtained now phenomenologically, heuristically. Okay, someone gets into some lab, does 3 experiments, and measures this, observes that. Now, the new applications that we're talking about, fracking, CO2 sequestration, nuclear repositories, and so on, require that we know permeability from a much more fundamental notion than just phenomenology. So I'm going to be showing you some of that. How do you get permeabilities in a much more fundamental way? I'll skip that. And finally, you need, say, finite elements to integrate all of this at the engineering scale and solve boundary value problems or engineering problems. So that's the theory. Let me show you some applications. No more equations, I promise. So let me show you one application that DOE was very interested in, because it relates a lot to these issues that we're talking about. This is an academic application, but you'll get the point. So remember, I told you that flow is extremely important in these applications. You're trying to extract fluids from these formations or inject them. Now, there's this formation here in Nevada called the sandstone from the Valley of Fire. This is a sandstone formation. There's a person standing here. And there are these structures here that you can barely see probably. There are these vein-like structures. They're called compaction bands. They're tabular zones of about a couple millimeters, or centimeters rather, about an inch in thickness. And they go deep into the formation. So you're seeing them go into the page. Many, many meters, perhaps even kilometers into the formation. And what geologists have always speculated is that these tabular structures will alter the permeability of this formation. Why? Because when they do SEM images, so if you keep zooming in, this is a specimen in the lab. This is a piece of rock extracted from this area. And these are SEM images, okay, microscope images inside the compaction band, inside this tabular zone, and outside. And black here is empty space. White or gray is solid grains. So you can see clearly that outside of a band, you have a lot of empty voids, space available for fluids to travel. Inside of a compaction band, not so much. So people had speculated that these formations will effectively form barriers to flow. And since 60% of our oil reserves in the US are in sandstones, that we needed to understand the impact of these formations and so on. So I'm going to show you an application of how we do that in a fundamental way rather than in a heuristic way. So people had come here, taken field trips, and speculated, oh, there's going to be a 3 orders of magnitude change in permeability. You know, and you would ask them, how do you get that number? And they'll say, well, you know, you go there, and we have some information about the geology. And I mean, they could never really get you an answer that was satisfactory. The best they could do is do some samples in the lab. And that wasn't satisfactory because the samples in the lab form compaction bands that are fundamentally different from the ones in the field. So what we finally decided to do was to bite the bullet, take a core from this formation, take it to the synchrotron in Chicago, and really measure permeability in a rather fundamental way. So let's take a trip to Chicago. This is the synchrotron facility from DOE in Chicago, Argonne. It's a beautiful facility. And here I'm going to show you an application of using this technology to really get an answer like never before to fundamental questions like what is the permeability of these formations, really from a fundamental point of view rather than phenomenology or guesswork. So let's see how that's done. So here's our core. Our postdoc went to the Valley of Fire and got a little piece of rock around this compaction band. This CB is a compaction band. So he's coring part of a compaction band and part outside of a compaction band. Here you see 1 and 2. Here is a cross-section of that 1 and 2 subsamples. This is a little cylindrical sample. You cut it with a diamond drill, a diamond bit, and you extract a little cylindrical sample. Here's a cylindrical sample. This number 1, again, is inside the compaction band. Number 2 is outside the compaction band. Check it out. Here's the porosity map outside of a compaction band and inside of a compaction band. It drops from 21% outside of a compaction band to 14% inside of a compaction band. So you have, what, 5% porosity change due to this formation, due to this compaction bands, okay? Not that dramatic. This is a cross-section, again, inside compaction band here, outside compaction band. You see that there are a lot of less pores available to you inside of a compaction band than outside. Outside, clearly more pores. Great. There is a qualitative difference in pore structure, but what does that mean for permeability? I mean, that's what you're interested in. And people could show you all these pictures have been available for the last 5 years. People have been taking beautiful pictures of these formations, showing that clearly there's a difference in porosity, but no one can ever say what's the change in permeability, say. So in order to do that, you need to do a little more work. So what you do is you take a CT image or a synchrotron image like the one I just showed you. This is, let's say, an example of that. And then you superimpose a mathematical tool that we call level sets. Level sets allow you to distinguish the solids from the empty spaces. Okay, so blue here is solid, red is empty, roughly speaking. And from that mathematical map, we're able to establish the skeleton of a pore structure, which is what you see here in this cartoon. So red here is pore, and you see that there's a corresponding spine-like structure here that tells you what the skeleton of that structure is. Okay, and that's called the medial axis. So once you extract the medial axis in these formations, you have like this is like looking at the map of a metro in DC. Okay, now you know where things go or where could they potentially go. For example, this guy's interesting. This guy is what's called occluded porosity. See this red spot here? That's porosity, but it's useless. It's not connected to anything. See, its spine doesn't connect anywhere. So this kind of information allows you to see what is useful porosity. Say, this is useful porosity. I start here, and I can end all the way up there. But if I push something through here, this porosity doesn't contribute to that at all. So in the permeability equation, it doesn't come in at all. So our goal here is to go from Boltzmann to Darcy. Boltzmann, or lattice-Boltzmann, is the method that people use in order to compute flow at the pore scale level. And Darcy, remember that Darcy equation that I showed you is the equation that people use to compute flow at the macroscopic level. So you want to go from the pore scale physics all the way to the continuum macroscopic physics, where engineers are really determining how much oil they can extract from this formation. So doing things at the pore scale are useless if you cannot scale them up. So we have come up with procedures that can allow us to push things up, right, building these sophisticated mathematical tools. And the goal here is to understand injection, withdrawal, and storage of fluids, of course, in this porous media. OK, I'll skip that. Let me show you the differences, other things that you can get from these methods. So again, when you look at the cumulative probability in grain diameter in these formations, inside and outside, you see that they're basically the same. That means that your rock inside and outside of these formations has the same diameter in the grains. Nothing is breaking too much. The grains are fairly intact. What does change a lot is the probability distribution of the tortuosity, for example. Right? Things are a lot more difficult to navigate inside the compaction band than outside. Tortuosity means roughly how long it takes you to go from one end to the other. So it's a lot more tortuous inside than outside. That's why it's difficult to transport fluids. This is a cartoon of two sub-samples from inside the band, outside the band. You see that inside the band, these are flow channels. These are paths that the water takes, or the fluid takes, to go from site A to site B. Very few, whereas outside the compaction band, you have a lot more. Now, this is probably my favorite picture from all this study. It's that you have two kinds of porosities. Again, connected porosity, occluded porosity. Connected porosity is useful porosity, good porosity. Occluded porosity is useless. Okay? It doesn't take you anywhere. Okay? Now, you can see that the connected porosity it's reduced quite a bit inside of a compaction band relative to outside of a compaction band. And that's the one that is controlling the permeability. But at the end of the day, when you do your permeability studies, this is a simulation using computers. So this is a mathematical model of flow. So we inject our fluid down here at this phase, and we watch it get out from the opposite phase by a pressure gradient. And the other four phases around the cube are not allowed to seep any water. So this is what's called a permeability test. We do a permeability test on these samples taken from the actual rock. This is an actual rock sample, but we're doing a computer simulation of a test. And we get permeability measurements of about 10 to the minus 12. When we compare it with inside of a compaction bed, you see a lot less water able to go from A to B. Right? The blue stuff here is water. Right? You see that the permeability drops by an order of magnitude, but it's not the 3 orders of magnitude that people were speculating before. It's only 1 order of magnitude, even though you have changes in porosity, say, from 20% to 15%. So there are changes, but they're not as dramatic as people thought they were. And now this is not a speculation. It's an actual fundamental measurement of the permeability. So we're able to do this. We're able to piece them together, all of these little cubes. We piece them together into larger and larger specimens, and we're able to see what the permeability is at the larger scale. OK. Yes, sir?
In doing the flow calculations, do you have to take into account zeta potentials and, sort of the microfluidic surface to volume issues?
We don't take that into account. We do take into account friction between the fluid and the solid, but that's about it. Now, let me take you to France, to the European radiation, European Synchrotron Radiation Facility, ESRF. And this is the other synchrotron in the world. So there's the Argon, there's the European, and they're very powerful. And here I'll show you some things that we're doing that go from Newton to Cauchy in terms of deformation, real quick before we close. So the idea here is to understand how these materials behave, again, from the very low scale, in this case, the granular scale, all the way to the continuum scale. These granular materials are controlled, remember, by the interaction between the grains. And if you could see those interactions, perhaps you could extract what we call the micromechanical state. And then from that micromechanical state, you could come up with some key variables, let's call them plastic internal variables, that control the physics at this scale. and then pass them to models that take those variables and can tell you what the behavior of the material is at the continuum model scale. So you're coarse graining, if you will. You go from something discrete, from Newton, right, from F equals ma interactions type, to something continuum where Cauchy stresses and things like this control the behavior of the material, right? Yet it's the same material, so you're trying to extract information from its discrete reality to some abstraction that looks continuum. So how do you do that? You go to a synchrotron facility, and you do experiments, for example. This is a cross-section of an experiment. It's about 2 centimeters high by 1 centimeter in diameter. It's being compressed as you watch this movie. Okay? And what you see here are grains of sand that are moving in real time as you're compressing this sample. Okay? So what's going on here? So let's do a zoom in here. This is more details of that experiment. So this is a cylindrical sample. You're seeing half of that here, okay, in 3D with thousands of sand grains stuck into a little chamber into the synchrotron facility and being pancaked, if you will, in the vertical direction. And as you're doing this, you're reading in the usual way forces versus deformations macroscopically. But at the same time, you're shooting X-rays at this thing. And you're watching how grains move from stage 1 to stage 2. All of these guys are stages where you took a tomography of the sample. And you're doing it at sub-grain resolution. So this is like 6 micron voxel resolution, whereas your grains are about 0.5 millimeters in diameter. Okay, so you have hundreds of voxels per each grain in resolution. And you're pancaking this thing, and you're taking X-rays. So you can see where each and every grain goes from one station to the next. You can get the kinematics of every single grain in a way that it's never been done before. Now, experimentalists are very excited about that, but engineers keep asking, well, what do I do with that? Right? That's beautiful, but what do I do with all these little grains moving from one place to the other, right? Give me something useful. So that's where we come in. We take this data and we make it somewhat useful. We extract these kinematics that I'm telling you about. These are displacement fields that you get from this data. And you start extracting information. For example, one key information that we like to extract is called dilatancy. And then we use that evolution of dilatancy. Here's a curve showing you a typical evolution of that dilatancy to construct models. Now, here's the experiment. So here's the sample being pancaked. And it forms a shear, and it shears quite a bit here once it starts to fail. And what we do is we construct mathematical models that we call multiscale models. Here's that model, using finite elements, using the displacement data that the French get from their beautiful experiments, and then building these beautiful mathematical models that compare very well with the experiments. So this is the deformation of the experiment. This is the deformation of the model. And they're pretty close to each other. Yes, we're missing some pockets of accumulated deformation, but all in all, we're not doing that bad. And again, this model is not a phenomenological model where you fine-tune the parameters. This is all information extracted directly from the physics. Oh, and one of my slides disappeared. I had a low displacement curve that showed how closely the agreement was with the experiments. OK, we're getting close to the end. So let me just show you a few slides about cements. Remember, cements are very important because we produce a lot of it. And if we keep growing at the rate we're growing, we will need to pour a lot of cement in this world. So this is a cartoon showing the scales of cement, similar to the one I showed you before. So this is the typical cement or concrete that you see with sand aggregates and whatnot, right? So this is the mortar concrete level at the centimeter scale. Right? Then you go to the paste scale, what people call CSH. And then, so the paste, the CSH, is a glue that glues together, right, all of these aggregates. Now, the CSH is the most important component of concrete. It's what makes concrete concrete. Okay? So if you understood how CSH works, you could engineer new, greener concrete. So at the level 0, there's this theory that says that concrete or cement is globular or granular. These grains interact with each other, and they control the behavior of these cements. So what you can do with that information is go to that nanoscale. Here's a model using that nanoscale structure of cement. This is a supercomputer simulation of a nanoindentation experiment. So here's the tip of a nanoindenter pushing down on a sample of cement. And what you see here in color are stress chains, right? So you're clearly stressing the area around the tip of indenter. Now, this exact same experiment was conducted at MIT physically. Okay, there was a physical experiment. And so the yellow points here are the results of a physical experiment. And in nanoindentation, you measure a couple of parameters, hardness and indentation modulus. And we're testing two kinds of cements here, one at lower packing fraction and one at higher packing fraction. Okay? So you can see here that the yellow results, okay, show certain spread in the test data. And then we come with our supercomputer model, and we make a prediction of what the hardness would be and what the indentation modulus would be for those same packing ratios for this cement. And these are our predictions in blue here from the mathematical supercomputer model. Without fine-tuning, without calibrating the model to give you what it wants, to make a true prediction. Okay? And you can see that the data is not too far away from, let's say, quote-unquote reality, if you can believe results from MIT, that is. Okay. So we're getting close to the end. So let me just show you what I think the future brings in terms of fundamental research, not really technology. I'm not going to tell you what stock to buy. But you can probably guess. So really, we want to go, the next frontier is to go to chemistry and to link that chemistry with mechanics. So this is a beautiful animation up here from one of my postdocs of what you could see one of those. It's like a sugar cube being diluted in water. Okay, but here is the real pore structure of that sandstone that I showed you that we imaged in the synchrotron in Chicago, and you can see it diluting there in a reactive fluid, right? So if we could now take these chemistry tools that are working by themselves, if you will, at this point, and couple them with mechanics, right? Pressure, for example, will alter how quickly chemical reactions occur, and chemistry also will alter mechanics. Clearly, you see that pore structures are changing. That will alter the way in which fluid flows, and so on. So they're clearly coupled. So where we're going now is to really put together chemistry, flow, and mechanics to really take a very close look at fundamental processes, like what's happening really when you do fracking, right? When you have all of these processes together, what are you exactly doing? And perhaps if you understand that, you can engineer a new type of fracking that requires less water or perhaps less chemicals. Another very exciting area is the area of computer-aided modeling. So it's very hard to see from this image. I can see it much better in my computer, in my monitor. But what you're seeing here is on the left, what looks like a Lego model. It's not really a Lego model. It's a CT image of a grain of sandstone. So CT imaging is becoming mainstream in many applications, and in particular in geosciences. And many of the oil companies now are investing a lot of dollars in getting these images to extract beautiful tomographic images at the grain scale. But as I told you before, these images are useless if you don't know how to put them into a framework where they can give you quantitative answers. So what we're doing here at Caltech is taking these beautiful images and taking them to the next level. So for example, this is a mapping of the curvature of this grain using level sets, right, to really see the topography of the grain. And over here, you cannot see it, unfortunately, but this is a mathematical, a functional representation of a geometry of that grain using brand new technology. So now, oh, that's much better. So now you can see, you can capture grain morphology using mathematics in a way that's been that no one has ever done in the past, right? That doesn't work. So now you can go from a beautiful sort of artistic representation of a material to a mathematical model that now you can insert into a computer and use for simulation to get real quantitative answers. Right? And that's not so much the future, it's very much the present. And I think if I had to predict that these models would play a bigger and bigger role, right, as we start doing more and more complex applications, as we need to do for CO2 and for fracking. Okay, so let's leave some minutes for questions. So let me finish by saying that I hope that you have gathered here that these geologic materials are very, very important in the energy equation. Okay, they're neglected, unfortunately, but they're terribly important. Okay, we need to understand the coupling between the formation, flow, and chemistry in these materials in order to continue to extract fossil fuels as we move forward. Okay, so if there's a message that you can carry to your congressman, will be that invest more in basic research, right, so that we can understand the formation, flow, and chemistry. And the good news is that here at Caltech, we're developing models that are really allowing us to understand these coupled processes, and hopefully, with enough understanding, as you all know, we'll be able to invent new technologies. Thank you very much. I'll be happy to answer any questions.
To put this kind of into perspective, we're not talking about a Texas wildcatter. My number 2 son's a pretty good petroleum geologist. I've seen him bringing in 4 wells in 4 weeks. And over the time, he'd say, well, I won't drill here. There's gas there, but there's too much sulfur in it, and there's no place to take out the sulfur. A couple Christmases ago, he said, well, they just pulled the drill, and they went down 16,000 feet with a 20-inch casing, and then they started for the 18-inch drill. And their goal was at 25,000 feet. And the budget was for $880,000, and they were over budget, but they were still drilling. So this is not some small operation like you see in the movies. It's right. And a lot of money goes behind it.
How much gas gets left in these fracked wells? Is there anything you can do to improve the efficiency of extraction?
I don't know. I have some numbers for oil. I think there's something like 50% or a little more of oil that gets left, that it's easily recoverable, and then they just leave it behind because it's better to go to the next one. For gas, I don't have a number, but I'm going to guess. Is it less?
50 is a little high, and you can get a little more out at very great expense. A good deal of it.
Well, you can always get more out. You just have to invest more.
What's done is about 40%.
Okay.
Which says 60% of the oil you find is still in the ground.
Switching to cement briefly, I've heard of 2 kinds of greener cement. One is a company that claims to be able to take CO2 out of the air to make the carbonaceous material in the cement. Yeah. And the other is cement I can buy at my local hardware store that's 50% recycled concrete. Can you comment on those?
Yeah, those are very interesting 2 applications, and I would call them green. What we're talking about here is slightly different, right? We're talking about engineering new cements to, say, make them more durable or reduce their CO2 footprint. But yeah, those are interesting applications, and I would call them green cement. And I think that, I think you have gathered that my view is that you allow all of these technologies to develop because you need them all, right? So I'm particularly excited about the one that uses the CO2 for carbonation. I think that's very neat.
I'm going to follow up on the cement question. 15, 20 years ago, I used to do a lot of work in ceramics, and I would go to the American Ceramic Society meetings, and I noticed that there was a large amount of work being done on cement. It was a real significant. And I always had the question of how this is being used. I mean, what I see from your talk, it's real clear there's a lot of cement being made, and it's really important. But how do I know that this is getting into my roadways or whatever, or they're not doing it? I mean,
well,
how does this happen?
the quick answer is it's not. The cement industry and the civil engineering industry, for that matter, is extremely conservative. Right? There's very little research money available, and the bulk of it is invested in observational methods, breaking 10,000 samples and getting some sort of a curve and some sort of, someone puts more fly ash into it and seeing what happens. There's very little invested in fundamental research. Civil engineering and cement industry don't believe much in fundamental research. So there's very little investment in it. Yet, as you said, there's so much being produced and so much that could be improved. The problem is that cement has been around for a long time, right? And there is this perception that we really know how to make it. And we do know how to make it. It's just that we could make it much better, right? I mean, we've been pouring cement, no question about that. But we need to pour, and we can continue to pour more cement. That's not the question. The question is, how can we pour the cement we need to pour and minimize the CO2 footprint, right? And I don't think that we have that answer with the current technology. But there's a lot of reluctance to invest in research.
You could probably make a lot of money if you could solve the cracking problem of cement highways.
You mean the potholes? Yeah. Yeah. That's right. I get some phone calls about that sometimes, unfortunately.
Okay, so forgive me for the question. You said you work for one of the companies that's doing drilling for natural gas. Is that a joke or is that serious?
It's not 100% a joke. No, I don't work for them. I, of course, work for Caltech. But I do interact with these guys because they, as you can see, they're interested in the kind of things that we develop. So we do interact, but I wouldn't call that I work for them.
Okay, so the
and I don't always talk in any of those companies.
Okay, so the morbid curiosity question is, are you under simple non-disclosure agreement, or are you under non-disclosure and non-disparagement agreement?
I won't answer that question.
You mentioned a fracking operation of approximately 3 million gallons of water.
On average.
How great an area, or if it makes more sense, how great a volume of rock is actually fracked? And leading into the extraction question, how great a fraction of that volume of rock is actually made permeable?
Okay, that's a great question, and I don't have a direct answer to that. All I can say is that there are numbers that allow you to say how many gallons you need per length of well that is being fracked. So that's a more quantitative way of answering your question. So the amount of water is proportional to the length of well that you have. So there is a number. I just don't have that number with me right now. You can easily look it up. Right, but it's a relatively large number, and then what extent of a rock is being fracked is very difficult to measure, right? So you don't quite know exactly how much you're fracking, and these fractures are very localized, as you could see, but the permeability is enhanced substantially from that. So you're not fracking a very large volume of a rock. You're fracking enough in key locations to enhance the permeability quite a bit. Because what you do then is the shales have like pockets of voids, and what you're doing by fracking is connecting those pockets. So the interconnectivity between those empty spaces, these are like the occluded porosities that we were looking at. So that's what fracking allows you to do, is to connect a bunch of occluded porosities and extract very quickly.
How do you know when to quit fracking at a particular location? How do you know when it's enough?
I don't know, because I've never done fracking, but that's probably a question for the guys that actually do fracking. I'm guessing that you can see how much you're pumping out, and if you continue to frack and you're not getting significant measurable gains, then you quit, right? I mean, I would guess that that's the way it's done in practice.
You showed us an example about how studying porosity as basic research could help to learn about the barrier permeability.
Right.
What are some other examples of things you hope to learn certain abilities will gain from the basic research on porosity?
So I can tell you, for example, so again, we go back to the interaction with the oil companies. So I have many friends in BP. And so BP, for example, has a group of scientists now looking at porosity. And there are so many things that you can gain from porosity. Porosity controls a lot of the processes that go on, right? So they're interested in things like, you know, how can I understand, essentially what you're trying to answer here is how can I understand better how to push fluids in and out of these pore structures, right? And if you really stretch your imagination, that applies to so many applications, right? CO2 sequestration is basically pushing fluids through. Enhanced oil recovery is essentially the same thing. Fracking involves many of those processes as well. Nuclear repositories have to deal a lot with non-leakage. So the ability to look at the pore scale is very, very important to the extent that you know, companies like BP have their own on-site labs looking at that, Schlumberger as well, ExxonMobil, and so on, right? So they understand that that a lot can be gained by looking at that piece of a puzzle, right? And then you can gain that, you can come with that knowledge and do better technologies that impact things at the very large scale. But that's still a promise more than an action item.
We have time for one last question.
If I said 88 million, it was 880 million.
Okay.
Was the budget.
This gentleman right here.
There's one more.
Oh, I was just wondering if anyone has actually gone down to 10,000 feet and brought back samples so that your experimentalist counterpart can go check on your work.
I don't have those samples. I would love to have a sample from there. But you know, samples, yeah, you can always get samples. What we were trying to do there was really to first understand whether we could do it, right? So what I showed you today is sort of a proof of concept, and then you interact with the companies and you try to do things that may lead them to actually measure things that are useful to them, you know. So, can we take one more or we quit? What do we do?
We'll do one more.
Okay.
Secrecy
You-
and so forth.
you-
Cores and call it scanning. That's all public record.
That's right. That's right.
So do you have data from the geothermal drilling? Because they do pump water down there and get water coming up. They analyze it.
I haven't studied geothermal enough. I'm just starting to get an understanding of what it means and et cetera. But again, that's another area where flow of fluids through these porous materials is important to the energy question, and it's unquestionable that geothermal will play a role. But my understanding has been that that's going to be relatively minor, say, relative to gas, like fracking and things like that. Right, because not every site is amenable to geothermal energy. Right, you would have to find sites that are really. Okay.
All right.
Excellent.
Professor Andre, thank you very much.
No problem. My pleasure.